So we'll continue the discussion. Any use case instance, any problem? Actually, some applications when we go further when we try to apply when we go for any topics, then we require these expressions actually. So as such, I am not able to give any use case pertaining to this, but this information is very much required. Yeah, one simple definition like this is saying what we are familiar. That is, we know the independent events P of A intersection B equal to P of A into P of P. Then A, B are called as independent events. If you remember, P of A intersection B equal to P of A into P of P. That means joint equal to product of separate. The same applies here. So the joint distribution function of xy is product of marginal x into marginal y. Then the random variables are called as independent random variables. Same case continues. So joint probability density function equal to product of marginal with respect to x and marginal with respect to. So then they are called as independent random variables. Discrete or continuous, whatever it is. I think this skip will go straight away into. Now we'll go through the topic, that is. Now I think we know about matrices, right? So now we'll spend some time on matrices, some concept called as eigenvalues and eigenvectors, which helps us to go further and discuss the concept principal component analysis. Now we know matrices, right? Suppose if I take 2, 2, 3, 1. Now in applications we might have seen like in data mining kind of stuff. So what is this 2, 2 stands for and what is this 3, 1 stands for? Well, it is nothing but a vector, right? So 2, 2 it is an attribute x. So one attribute which takes values 2, 2, and 3, 1 is another vector, another attribute which takes values 3, 1, which we can represent in terms of a matrix. Right? So this is a 2 by 2 matrix, right? This is now I take another column matrix or column vector. So now 2, 3 and 2, 1 is a matrix, and 3, 2 is another matrix, and I do the multiplication here. So I hope we know how to multiply this. So then we are getting 48. Now how we multiply is very simple here. So this row into this column, 2 into 3, 6 plus 3 into 2, 6, that is 6 plus 6, 12. Next row is this row and this column, 2 into 3, 6 plus 1 into 2, 2, 6 plus 2, 8. Now this I can write as, if I take 4 outside, then I can write, or I can get 4 into the same x here. So here why I am trying to have this is, now I am trying to have a combination or arrangement or transformation of matrices such that if you see here, A is a matrix, right? X is another matrix, lambda is some scalar, and I am getting x. That means I am looking for a transformation such as Ax equal to lambda x. Right? So this is my interest. Ax equal to lambda x is my interest. That means I want to have the transformation of vectors or matrices with an arrangement that is Ax equal to lambda x, where x is a column vector or column matrix, A is a matrix, and lambda is the scalar. So if I am able to have this, then some names are there. So lambda is called as eigenvalue and x is called as eigenvector, and this matrix is A is the transformation matrix. Okay. This is the basic definition. Right. So whenever I have Ax equal to lambda x, then lambda is called as eigenvalue, x is called as eigenvector. Now, what is the significance of this? Right? So, what is the significance of doing this? Any idea? If you had any idea, what is the significance of? Yeah, eigenvalues are close. Yeah, that is one observation, right? Yeah. So here actually two types of, whenever we had a vectors, particularly if you take a vector, two types of transformations we look for. One is the scaling, other one is rotation, right? You see, suppose vector in the sense, suppose if I take, right, this is some, suppose x, y kind of thing. Suppose here I had a vector. Okay. Now I'm not going in depth, just I will touch upon. Now this is another one vector, right? So most of the times whenever we deal with vectors, we require two types of transformation. One is the scaling of this, right? And the other one is rotation of this. Right? One is the scaling, other one is rotation, right? So here the eigenvalues, eigenvectors concept helps us when we want to scale it. Right? That is one point to add here. So rotation, so it won't help us. Eigenvalues won't help us with respect to rotation. Here eigenvalues helps us where we require scaling of the vector with in the direction of so and so, and in terms of a scalar, that is the multiples of a scalar lambda. Right? This is the simple definition of the concept related to eigenvalues as well. So mathematically, if you ask me to define, this is what I define: x equal to lambda x, where x is called as eigenvector and lambda is called as eigenvector. Yeah, I will share one or two problems. Now, simple example. Simple example. Yeah, both x are not the both x are the same. That means here actually we want to have such an arrangement: a matrix A and x and this x are the same, and this lambda is. So we want to have a transformation matrix A and a column vector x and a scalar lambda such that Ax equal to lambda x. Both are the same. Then this lambda is called as eigenvalue and x is a corresponding eigenvector. Now simple example what I have taken is, so what actually it makes is, suppose if I take a matrix 9, 4, 4, and suppose if I take x5. Literally what happens here? Now it is, if you see, this transformation is nothing but 9x plus 4y and 4x plus 3y, right? I'll come to the next. I'll come to the point x. What is the dimension of x? Because the matrix here, the matrix is a 3 by 3 matrix, and you have x, y, z. Then you have 3 by 1. If the matrix is 4 by 4 matrix, then you have 4 by 1. But always it is a column vector or column matrix. That's why it is n by 1. Here n equal to 2, therefore it is 2 by 1, 3 by 1, 4 by 1. A simple point to understand. Suppose if I take A as this, the transformation matrix as this, and the column vector as x5. That means my transformations are 9x plus 4y and 4x plus 3y. And what it happens is, suppose I take some points 0, 0, 1, 0, 0, 1, minus 1, 0, 0, minus. These are my original points. Okay. And if I plot all the points, I will get this 1, 0, 0, 1, minus 1, 0, 0, minus 1. Right? This is. Now what I am doing is I am using this transformation. then what happens here is my 0 0 if I substitute, then it becomes 0 0. If I take x equal to 1 and y equal to 0, this becomes 9 4. Similarly 4 3 like this. That means, so this actually circle which I have taken is becoming some kind of ellipse here. Right? So that means what we are doing, we are scaling it. If you see here, so this we are scaling it to some level. Right? Similarly, this we are scaling. Right? So actually, that is where the eigenvalues, eigenvector concept helps us. Right? When we want to scale the vector in a given direction. Here, the eigenvalue gives the magnitude and eigenvector gives in the direction in which we are going to have a scaling. Actually, in math, it is a 2 to 3 hours topic we discuss. Now, where 4 comma 3, this is like 4 comma 3 somewhere here, and minus 4 comma 3, minus 4 comma minus 3 somewhere here, 4 comma 3 somewhere here, somewhere here actually. So my intention is that just to show this, actually this is a circle, and with the help of transformation, what I am doing is I am scaling this too. That means suppose if I take a vector here, then suppose if I take a vector 2 comma 1 kind of thing, then it is scaled to this. So then in that what we require is what is the eigenvalue, that is how many times you are scaling it, and in the direction of which vector. I hope that you got it. So this I want to scale it. Okay? So then I need the help of eigenvalues and eigenvectors to say, so what is your lambda, the scaling factor, and what is the direction of that scaling. So that is where eigenvalues as well as eigenvector helps me. So that's why I'm not going much deeper into this math related to matrices, just to understand. So eigenvalues as well as eigenvectors helps us to scale the vectors. It helps us to scale the vectors, where eigenvalue helps us with the magnitude and eigenvector helps us with the direction. So I hope that at least it gives some understanding in terms of eigenvalues as well as eigenvectors. Now just how to find it. How to find it. So for a given matrix, how to find the range? Actually, this transformation matrix is known. Then we have to find what is the scaling factor and what is the direction, such that we get Ax equal to lambda x. Yeah, eigenvalues and eigenvectors both helps us. Yeah, eigenvalue helps us. That eigenvalue is nothing but the scaling factor. Eigenvector is nothing but the direction. So both helps us in terms of scaling. Now mathematically how to find, because actually don't be scared of the calculations. Right? So it's very easy to I'm not going to say that you have to solve it by using pen and paper, but you have to have a clear understanding with respect to eigenvalues and eigenvectors and how to find it. When we try to implement in terms of either any of the implementations, it is very easy to get the corresponding eigenvalues as well as eigenvectors. Yeah, scaling is nothing but the magnitude of it perfectly. Now, how to find? Just we'll quickly go through the math behind the eigenvalues and eigenvectors. Again and again, I repeat, don't be scared of the math, what I am going to explain, right? But better to understand the process. And I'm not going to trouble you by asking a question in which you have to find eigenvalues as well as eigenvectors, because it takes a lot of time if you try to find eigenvalues and eigenvectors, if it is a 3 by 3 matrix at least. It is a more time consuming. I am not going to trouble you. But at the same time, you have to understand it very clearly. Now, this is what we have been telling, right? We want some arrangement Ax equal to lambda x, right? We want an arrangement Ax equal to lambda x such that a scaling factor and scaling direction also can be helpful, can help us, right? So how to find it? So very simple here. Now I'll write this as a minus lambda I into x. Why I go for I is this. If I take lambda, it doesn't make any sense. That's why without losing the generality, just I am multiplying a matrix by identity matrix. Identity matrix doesn't affect it when I multiply. Now we are getting a minus lambda I into x equal to 0. This is what we have. Right? So that means we need to find x values as well as lambda values. So this is what we call as the system of equations which are homogeneous. This is like very simple actually. A is a matrix, lambda is some value, I is our identity matrix like this. It is a 2 by 2. Yeah, I will tell you. 1 0 0 1 is 2 by 2 identity matrix, and this is 3 by 3 identity matrix. Why? That is a very good question actually. Why I need to multiply with I? Because after taking Ax equal to lambda x, now I can write this as a minus lambda x equal to 0, right? Now I want to take lambda outside, right? Then a minus lambda into x, right? A minus lambda into x. Do you feel it makes any sense? Because from a matrix I am taking a value outside, right? From a matrix I am taking, that is from a matrix 2, 2, 3, 3, 4. I am taking one element out. It doesn't make any sense. So that's why we multiply here with I. Because multiplication of any matrix with I doesn't affect it. Because I into x is always x. That is the reason. So where we use it, actually this is a very, very important concept. Many practical applications are there in terms of eigenvalues as well as eigenvectors. One is the next whatever we are going to have dimensionality reduction or principal component analysis depends on eigenvalues as well as eigenvectors. So that is same, I think I will tell you. One is those who are already familiar with respect to data mining. I think you might have had a discussion in terms of dimensionality reduction. Right? Dimensionality reduction, I think their eigenvalues, eigenvectors helps us in reducing the dimensionality of the data. This is a very important concept in terms of data science. Yeah, in game development, in image recognition, particularly in actually before data science coming into picture, people use this concept in image processing and pattern recognition kind of applications. Right. Simply now what we do is, now this is one system of equations like this. A is a matrix, 1 is identity matrix, lambda is some value, 1, 2, 3 kind of. Yeah, this is a matrix, right? And X is a column vector is containing variables now because we are going to find variables. That means we'll get equations. Example like this. Right? Based on the concept what we had in matrices, we had two types of solutions. One is trivial or zero solution, other one is non-trivial solution. So this is homogeneous system which will have non-trivial solution when determinant equal to 0. Because nothing to do with this is always a guaranteed solution. Only thing what we try to find is a non-zero solution. So where this condition is applicable to find non-zero solution. Now we'll see this example. But don't be scared of if you are not able to follow this discussion. So suppose A is a matrix. Now we want the arrangement X as well as lambda such that Ax equal to lambda X. That means for what values of scaling factor lambda and corresponding X, I can have this Ax equal to lambda X. So that is the idea here. Okay. So as discussed here, A minus lambda into 2 by 2 identity matrix. Then I will take the determinant. So 0 minus lambda, 1 minus 0, minus 2 minus 0, minus 3 minus lambda equal to 0. And get off A minus lambda equal to 0. If I simplify, that is, I think we know how to find determinant. So here in this case, very simple, AD minus BC. So maybe I'll try to share some information related to matrices separately, so that those who are not able to understand, you can go through it. Why one is subtracted with, now this is what we have been A minus lambda into I. I is identity matrix, right? Identity matrix. Now this is how matrix addition or matrix subtraction we do, right? 0. Now if you multiply by lambda, then here lambda comes, here lambda comes. Then 0 minus lambda, 1 minus 0, minus 2 minus 0, minus 3 minus lambda. Therefore, this. So once we have, then it is the then it is AD minus BC, very simple. Then suppose we are getting this equation. So if we solve this, we'll get lambda equal to minus 1, lambda equal to. That means, so these are the scaling factors. Right? Lambda equal to minus 1, lambda equal to minus 2 are the scaling factors. Now, if these are the scaling factors, then what are the corresponding eigenvectors? That is, what are the directions in which we can scale it with a factor minus 1, with a factor minus 2. So then what we do is, we have to find separately. When lambda equal to minus 1, what is its corresponding factor or vector? Similarly, when lambda equal to minus 2, what is its corresponding eigenvector? So how to find this is, when lambda equal to minus 1, so that means here take as a matrix, put lambda equal to minus 1. That means here 0 plus 1, 1 minus 2 minus 2 into x equal to 0. Suppose x equal to x1, x2, some unknowns, then what we get is x1 plus x2 equal to 0, minus 2x1 minus 2x2 equal to 0. And if you see here, both are the same equations. That means both becomes x1 plus x2 equal to 0. So when x1 plus x2 equal to 0, then because we can't have a separate simple solution, here we get infinite number of solutions which satisfy 0. Therefore, we assume, suppose if you take x1 equal to k, then x2 becomes minus k. Therefore, the corresponding eigenvector is k comma minus k. So from this we can have any eigenvectors. For example, here what I have taken is k equal to 1. If we take, then 1 comma minus 1 is the eigenvector. Similarly, by repeating the same procedure, lambda for lambda equal to minus 2, we'll get another eigenvector. So here don't be scared of this. Just try to understand the process involved in it. Because actually, if you 3 by 3 matrix is given, where suppose you have to find eigenvalues, eigenvectors, it becomes a lengthy calculation here. But understand what is eigenvalue, what is eigenvector, how to find eigenvalues, as well as how to find eigenvector. Okay, I will explain now. Now I repeat here. Actually, I am scared of actually because it is more of calculations. Now I repeat this. So now this is the matrix where we want to find the combinations of lambda and corresponding x such that x equal to lambda x. Right? So for which, based on the previous discussion, so that condition what we use is this, right? Get of a minus lambda equal to 0, right? Okay. No, actually, there won't be much clear courseware here because it is more into math kind of. I will share it, no problem. I will share with one or two examples. If you are interested, you can go through this. So a minus lambda equal to 0, where here a minus lambda is a constant and I is our regular identity vector I1 0 0 1. Now what we have done is multiply this by lambda and go for addition or subtraction, whatever is there in between. Therefore, it is 0 minus lambda, 1 minus 0, minus 2 minus 0, minus 3 minus lambda. Therefore, this is what we call as determinant, which is equal to 0. Now we expand this determinant. It's a simple determinant where it is AD minus BC actually. This is AD and minus BC. So 0 minus lambda into minus 3 minus lambda, minus of minus 2 into minus 1, therefore it is between plus 2. And if we simplify this, we'll get this lambda square plus 3 lambda plus 2 equal to 0. So if it is P by T, actually the calculation, the simplification is time taking, time consuming. You will get a cubic equation here, lambda cube plus 3 lambda square minus 2 lambda plus 4 equal to 0. Like this, we'll get a cubic equation. Now, if we solve this equation, we'll get two rows. This can be written as lambda plus 1 into lambda plus 2 equal to 0. That means lambda equal to minus 1 and lambda equal to minus 2. That means for this matrix, we have eigenvalues. Now we need to find for this lambda what is the x that gives us this arrangement. Okay. That means once we have lambda value, for each lambda we have to find x such that we will get ax equal to lambda x. Okay. So how to do it is, now we had ax equal to lambda x, right? Now take lambda equal to minus 1 and a what already we had. Then we have to solve it for x. So we'll see it how. Now ax equal to lambda, just like what we have been discussing yesterday. Here ax equal to lambda x, then the matrix is a minus lambda I into x equal to 0, right? Same we use here. A minus lambda I into x equal to 0. Lambda equal to minus 1, therefore it becomes 0 plus 1 and now we need here our aim is to finding x value. What is x? It is a column vector or column matrix. Suppose that column matrix is x1, x2. This is. Now if you see here, this is 1 and 1. That means 1x1 plus 1x2 equal to 0. Second one is minus 2x1 minus 2x2 equal to 0. If you see this, both are the same here. If we take out minus 2 here, then which is nothing but x1 plus x2 equal to 0, right? That means both are reducing it into x1 plus x2 equal to 0. So from this we want what is x1 value, what is x2 value. If you remember many combinations, right? Suppose if I take x1 as 1 by 1, x2 is minus 1. Right? If I take x1 as 1 by 2, x2 is minus 1 by 2. Suppose if I take x2 as 1, x1 as minus. Like this, how many x1s and how many x2s will have? Infinity. I think many. That's why in all these cases we will get infinite number of solutions. So how to get it? Very simple. Assume let x1 equal to k, or either way x2 equal to k. Here I took x1 equal to k. When x1 equal to k, x2 is minus k. That means this is my eigenvector. So from this, you can give any value to k. Suppose here in this case, I have given the simplest value for k, that is k equal to 1. Therefore, 1 comma minus 1 is my eigenvector corresponding to lambda equal to minus 1. Okay. Now similarly, I think I have not done the calculation, I think. So similarly, repeating the same process for lambda equal to minus 2, we will get another or corresponding eigenvector. Okay. Okay. So if I think I hope I understand. I think maybe for most of us still it is not clear, but I will try to share some more regarding in terms of this because completely it is a math kind of stuff. So even how to find these values also, right? I'll definitely I'll share with one or two examples, but this is for your understanding purpose. Not that I'm not going to ask a question on this, but this is a very important concept you need to understand. I hope that now it is clear, right? What is eigenvalue? What is eigenvector? Right? How to find eigenvalue? How to find eigenvector? So whenever we remember eigenvalue, eigenvector, immediately what should we recall is Ax equal to lambda is. Lambda is the scaling factor, and x is the, that is nothing but magnitude here, and x is the direction. Now, that's the principal component analysis. So here in the principal component analysis, what is this principal component analysis? Any idea? Like, yeah, we'll break for a few minutes, then continue with principal component analysis. Yeah, very good.